morning, one and all. Myself, Sreevani, working as an assistant professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. So, in the today's lecture, we are going to learn about oblique incidence at a plane dielectric boundary. So, before going to discuss about this oblique incidence at a plane dielectric boundary, so let me introduce first how many types of incidences occur. Then from that, how many cases we have analyzed. Now, the new thing we are going to learn in this particular lecture is oblique incidence at a plane dielectric boundary. Right? So here, firstly, there are two types of incidences over there. One is normal incidence and second one is oblique incidence. So oblique incidence, before going to discuss about this oblique incidence, firstly we have already learned in the previous lectures as related to this normal incidence. So under this normal incidence we have discussed two cases as normal incidence at a plane dielectric boundary and second one is normal incidence at a plane conducting boundary. Normal incidence at a plane dielectric boundary and normal incidence at a plane conducting boundary we have discussed. Now coming to the oblique incidence means there exists some object which is separation between two media is occur and that can be we have considered here at z is equal to 0 plane, right? So means at z is equal to 0 interface or the boundary is exist at below z is equal to 0, that is z less than 0 case we have medium 1 and above z equal to 0 means if z is greater than 0 case we have medium 2, right? So in this oblique incidence at a plane boundary case, here also we have two different classifications are there. Oblique incidence at a plane dielectric boundary and oblique incidence at a plane conducting boundary. Right? So now we will discuss here related to this oblique incidence at a plane dielectric boundary case. Okay? So now to derive the equations or mathematical expressions for this oblique incidence at a plane dielectric boundary, firstly we have considered two dielectric medium case. One is medium 1 is to be dielectric medium and medium 2 is also dielectric medium. Okay. So between two dielectrics we are going to analyze means we will place one, we have one objection that is comes under oblique incidence at a plane dielectric boundary. Means in both the medium we have select the mediums to be dielectric mediums only. So for the dielectric medium as we know that sigma equal to 0. For conductivity of that one is equal to 0 for the perfect dielectric medium. As we know that perfect dielectric medium is sigma equal to 0, that is also called as lossless dielectric medium, right? So in order to derive the mathematical expression for this oblique incidence at a plane dielectric boundary or conducting boundary case, firstly here we have considered the first case as a dielectric boundary means both the medium 1 and medium 2 are considered as dielectric medium. As we know that for a perfect dielectric medium, its conductivity equal to 0. Hence, if sigma equal to 0, alpha equal to 0, then alpha 0 means there is no attenuation, there is no reduction in the amplitude of the signal. Hence, that perfect dielectric medium is also called as lossless dielectric medium, right? So, in order to analyze that one first, what it consists of, what is there in the medium 1 and what is exist in the medium 2. So suppose if we consider in the medium 1, the characteristic parameters are epsilon 1 and mu 1 along with that sigma 1. Similarly, in the medium 2 also, the characteristic parameters are epsilon 2, mu 2 are exist. As we know that epsilon and mu are the two characteristic parameters of the given medium is dielectric medium, that is permittivity and permeability of that respective medium, right? So in order to analyze this one, firstly, we are going to consider one incident wave, right? So when the incident wave strikes the boundary, part of this incident wave is reflected back to the same medium, that is ER, and part of this is to be represented with ET. Means where incident wave EI is a combination of reflected as well as the transmitted wave field strengths, right? So depending upon this, means when the incident wave touches the boundary or strikes the boundary, part of this incident wave is reflected back to the same medium and part of this incident wave is transmitted to the next medium, right? So next medium means in the medium 2. So suppose if you observe in this figure, in medium 1 we have two traveling waves. One is incident wave and the other one will be reflected wave. And in the medium 2 we have only the first one is exist, that is transmitted wave only, right? So this is incident wave, means this is reflected and reflected wave, and let it be this as transmitted wave. Okay. As we know that EI is the notation for electric field intensity vector for the incident wave, and ER is for electric field intensity vector for reflected wave, and ET is transmitted wave electric field strength or intensity, right? So consider that a uniform plane wave is incident obliquely, means in between two media there must be some objection, means when the incident wave strikes that objection or touches the boundary, part of it will be reflected back to the same medium and part of it is transmitted to the next medium. Means consider that a uniform plane wave, nothing but electromagnetic wave, is incident obliquely at the interface between the two dielectrics. As we know that for a dielectric medium, sigma equal to 0. Next, the two dielectric media are assumed to be lossless, perfect dielectric medium, with different constants such as mu1 epsilon 1 for medium 1 and mu2 epsilon 2 is for mu2 is for medium 2, right? So consider here two dielectric media and two are characterized with the respective characteristics parameters as epsilon 1 mu1 for medium 1 and epsilon 2 mu2 for the medium 2, right? So in order to analyze that, firstly we will consider one simple figure. So this figure consisting of this is x direction, this is z direction. So and when the incident wave, this is ANI, incident wave direction, incident wave. Okay, and part of this is reflected back to the same medium. Part of it is reflected back to the same medium, means that wave is said to be here reflected wave, right? And the direction is to be considered as ANR. R stands for reflected wave, and part of it is transmitted to the next medium and it is represented with ANT. Small a is the notation for unit vector and normal to that is resembles with N, and T is for transmitted. Okay, and this is transmitted wave. Now, when the incident wave making angle, if you consider it as theta I, and this is reflected wave field making angle as theta R, and there exists one and the intersection points are considered to be here. This is O dash, let it be this is O, and there exists intersection point which is exist from O to this is A, and another intersection point which is exist between O dash and this is represented with A dash, and from O dash to we have considered another intersection point, let it be this is B. Okay, so this is theta I, theta R, and this one is theta T. right? So if this is to be considered as theta t, and this angle considered to be as 90 minus theta t. Why? Because the angle between this is exactly represented with 90, and adjacent angle in that right right angle triangle, it will be 90 minus theta t. And similarly, if this is theta r, this will become 90 minus theta r. Okay, and intersection points are to be considered along with the points, means this is transmitted wave. Okay, so oblique incidence at a plane dielectric boundary case. Dielectric boundary, right? So now, see, if we observe, first consider in the medium one, let it be first. Medium 1, this is medium 1, and here it will be the medium 2, and in the medium 1 characteristics are epsilon 1, mu 1, sigma 1, and for medium 2, epsilon 2, mu 2, sigma 2. Okay, so in order to analyze this one, firstly we have considered oblique incidence at a plane dielectric boundary, and where this boundary is exist at z is equal to 0. Below z equal to 0, medium 1 is exist with the characteristic parameters are epsilon 1, mu 1, sigma 1, and with medium 2, epsilon 2, mu 2, sigma 2. Okay, and theta, incident wave making angle, is considered to be here theta I, and for reflected it is theta r, and for transmitted it is represented with theta t. So where ANI stands for representing incident wave vector ANI. Similarly, for reflected wave, it is represented with ANR, and for transmitted wave, it is considered as ANT, right? So, if you observe particularly in this figure, in the medium one, we have two traveling waves. One is incident wave, and the other one will be reflected wave, right? And in the medium two, there exists only one transmitted wave, right? So, depending upon this, we can write, when the incident wave strikes the boundary, part of it is transmitted to the next medium, and part of that incident wave is reflected back to the same medium. So in the medium one, we have two traveling waves. One is considered, means E1 is equal to EI plus ER. And if we observe in the medium 2, that electric field intensity vector E2 is given by here ET only. Why? Because in the medium 2, part of the incident wave is exist, that is called transmitted wave. It is also called as refracted wave. It is also called as refracted wave. So there is a difference between this reflection and refraction, right? So this is called a reflected wave, and here transmitted wave is also called as refracted wave. Depending upon this figure, we will derive the mathematical equations for Snell's law of reflection and Snell's law of refraction. Okay, to derive that, first see, let the lines OA, O dash A dash and O dash B be the intersections of the plane of incidence with equiphase surfaces of the incident wave, reflected wave and transmitted waves, right? So from this figure, see, OA, this dotted lines representing one intersection point, that is for the incident wave, and another intersection point as A dash O dash is for reflected wave, and O dash B is the incident interface or intersection for the transmitted wave, right? So from that, see, let the lines OA, intersection point for the incident wave, O dash A dash is for reflected wave, and O dash B be the intersection point of the plane of incidence with the equiphase surfaces. Equal surfaces, phase angles must be same. So equiphase surfaces of the incident, reflected and transmitted waves are respectively. So OA is for incident wave, O dash A dash is for reflected, and O dash B is for ET. These two are exist in the medium 1 and this one is exist only in the medium 2. Remember that. Then the incident and reflected waves travel in medium 1 while the transmitted wave is traveling only in medium 2. Then the velocities for the waves in the medium 1 is same and let it be V1. Means the V1 is the velocity which is exist in the two waves velocity in the medium 1 and it is representing with V1. So if the velocities, if the waves which are exist in the medium 1 velocities are same means the distances those two are traveled by the waves are also same, right? So from that we can say here the distances. Those two distances how we can consider means OA dash and AO dash. The two waves which are exist in the medium 1 means incident wave and the reflected wave. The distances how we can calculate is AO dash is for reflected and OA dash is for incident wave, right? So two distances means two waves are moving in the same medium means velocities are same. If the velocities are same means the distances which are traveled by the two equiphase surfaces are also same, right? So from that we can say that means if the velocity, the waves which are exist in the medium 1 are same means these velocities are same means let it be, we will consider it as V1, and in the medium 2 velocities if we are representing with V2 then the distances which are given by those two are same, right? So those two distances are represented with OA dash and AO dash, right? So if the velocities are same, V1 and V2 are same and the distances, so velocity for the medium 1 waves, incident and the reflected waves are same means the distances which are traveled from those two waves are also same. From those two, we can say that OO dash sine theta R equal to OO dash sine theta I. How we can write on this one? First consider this is the triangle O A dash. First consider OA O dash triangle. This is the triangle. So for this, the reflected wave angle is given by here theta R. Means if this is theta R means this one becomes 90 minus theta R. If you write that triangle cosine function, cos of 90 minus theta R equal to cos of 90 minus theta R. So AO dash O is the triangle. So for this triangle, if you are writing cos 90 minus theta R, then function becomes cos theta function means how you are going to write the angle. So adjacent side by hypotenuse. So adjacent side of this 90 minus theta R is becoming here AO dash by hypotenuse as O dash. Okay, see here. See this. Cos 90 minus theta R equal to O A dash by O dash. From these two, we can write O A dash is equal to distance, no, it is also represented with vector. O A dash is equal to O dash into cos 90 minus theta R. Cos 90 minus theta is represented with sine, hence it is O dash sine theta R. That is O A dash is nothing but O dash into sine theta R. Similarly for incident wave is also we will derive the same. So here the distance O A dash is same with the A O dash distance. Means incident wave and the reflected waves are traveling in the same medium means their velocities are same. If their velocities are same means the distances which are traveled from this region means A to O dash and O to A dash are same. So from that we will be calculating here OO dash means OA dash can be written as OO dash sine theta r equal to, from this AO dash means OO dash sine theta I. So these are the two distances means we are representing with vectors. Now from this both sides these two gets cancelled, then sine theta r equal to sine theta I. Now from this analysis theta r equal to theta I. So what actually theta r is it? This one. So reflected wave making angle theta r is same as that of the incident wave making angle as I, right? So theta I equal to theta r. This is called as Snell's law of reflection. Okay. So what do you mean by Snell's law of reflection? So that we observe here. So from equation 1, what is that equation 1? Theta I equal to theta r is represented with, let it be equation number 1. So from equation 1, it is clear that the angle of incidence and the angle of reflection are equal. Angle of incidence is represented with theta I and the angle of incidence is represented with, reflected wave is represented with theta r. So from this we can say that the angle of incidence and the angle of reflection are same or equal. Then that is called as Snell's law of reflection. It is related to reflection. Snell's law of reflection. So the statement is given by here theta I equal to theta r. So Snell's law of reflection. From this oblique incidence at a plane dielectric boundary, we will derive two mathematical equations. One is Snell's law of reflection and Snell's law of refraction. So firstly we have got here Snell's law of reflection, that is given by here the angle of incidence and the angle of reflection of the waves are equal, right? So theta I equal to theta r from this statement. Now from the previous diagram, it is also observed that the velocities which are there in the two waves in the medium one are same. Then from that velocities we can equate distances which are traveled by two waves are same. Now velocities distances are same means the time taken to reach that distance are also same. So from that time taken parameter, see, it is also observed that time taken by the incident wave to travel from A to O dash in the medium 1 is equal to that time taken by the transmitted wave to travel from O to B in medium 2. A to O dash, see, if you observe, here is the figure, A to O dash. This the time taken to travel the incident wave from A to O dash and the time taken to travel the transmitted wave from O dash to B must be same. This A to O dash in the medium 1 is equal to the O dash to B in the medium 2. So this is related to incident wave and here it will be related to the transmitted wave. Right? The complete analysis is derived from this particular figure only. Okay, so it is also observed that time taken by the incident wave to travel from A to O dash in the medium 1 is equal to the time taken by the transmitted wave to travel from O to B in medium 2. So that is represented, see, in the medium 2, this is related to the medium 2 and this is related to medium 1. Okay, if the times are same means that according to the formula velocity equal to distance by time, right? So velocities are same, then distances are same, then time taken to travel, those two are also same. Depending upon that, we are going to write t equal to distance by velocity. What is the distance for the transmitted wave which is to be in the medium 2 is O to B to the velocity in the medium 2 is represented with V2 and the time taken to travel the incident wave in the medium 1, that is A to O dash in the velocity is V1, right? So depending upon this, the fundamental formula t equal to distance by velocity. Now O to B is the distance by velocity in the medium 2 is this V2 and in the medium 1 the distance is given by A to O dash and velocity is V1. Okay. Now from these two, OB by V2 equal to AO dash by V1. From these two, we can write OB by AO dash is equal to. So, how we have written the reflected wave and incident wave velocities, here also O to B means if you want to the transmitted wave to travel from the distance from O to B is equal to the OO dash into sine theta t. And AO dash is how we have evaluated in the reflected case, that is same, that OO dash into sine theta I means sine theta if you consider, then that becomes OB by OO dash, and for sine theta I it is given by, that is AO dash by OO dash. From these two, if you write OB bar equal to OO dash bar into sine theta t, and from this AO dash bar equal to OO dash bar into sine theta I. How we have evaluated in the first figure. Now OB bar by AO bar equal to OO bar dash into sine theta t by sine theta I. Right? So these two gets cancelled, sine theta t by sine theta I, which is equal to V2 by V1. Previous analysis, right? So sine theta t by sine theta I equal to V2 by V1. Now from this relation velocities, we are also have the one more relation for that is beta 1 by beta 2. What is this beta here? This beta is nothing but phase constant. So to relate this beta phase constants in the medium 1 and medium 2, we will have the first fundamental equation for the velocity of that electromagnetic wave is given by V equal to omega by beta, where omega is the angular frequency and beta be the phase constant. Right? So for V1, let it be V1 is equal to omega by beta 1 and V2 equal to omega by beta 2. Now if we substitute sine theta t by means sine theta t by sine theta I equal to what we have V2 by V1 equal to. What is that V2 here? Omega by beta 2 by omega by beta 1. So if you simplify this equation, omega by beta 2 into beta 1 by omega. This omega and this omega gets cancelled, which is equal to beta 1 by beta 2. So one more relation for this one is sine theta t by sine theta I equal to V2 by V1 equal to beta 1 by beta 2, and this relation is obtained from velocity V equal to omega by beta. Angular velocity, that is V equal to omega by beta. From the medium 1 and medium 2, two velocities are representing with V1 equal to omega by beta 1 and V2 equal to omega by beta 2. Now if you simplify that one, sine theta t by sine theta I equal to V2 by V1, which is nothing but beta 1 by beta 2. And where beta 1 and beta 2 are the two phase constants of the medium 1 and medium 2. Next, one more relation. Now to derive that one more relation for this one, we will consider, but for any medium, the ratio of speed of light in free space. Speed of light in free space to that medium. So is called as index of refraction. So that index of refraction is represented with the small n and it is given by C by V, where C is said to be velocity of light in free space and V be the velocity of light in the medium, respective medium, right? So n is equal to C by V, where n is called as index of refraction. Based upon this index of refraction, we will have another relation that from that we are going to get one more relation called Snell's law of refraction. Why it is called Snell's law of refraction means it is derived from the index of refraction. Okay, so that index of refraction is represented with small n, and mathematically we can write that equation as n is equal to C by V. Now for medium 1 means in general we will represent it with n is equal to C by V, and for respective mediums means for medium 1 and medium 2, Why? Because we are analyzing this one with oblique incidence at a plane. Dielectric boundary means two medium. Two media we have considered. That is, for the first medium one, index of refraction is represented with n1 and it is given by c by v1. And for medium 2, index of refraction is n2 equal to c by v2. Why c is common for both means where c is said to be velocity of light in free space, and v1 and v2 are differed with respect to the medium 1 and 2. So like that, n1 can be written as c by v1 and n2 can be written as c by v2, right? As we know that velocities from those two equations means sine theta t by sine theta I equal to v2 by v1 equal to. Now from these two relations means n is equal to c by v, from this velocity v equal to c by n. So if you want to write means in place of v by v1 and v2, then v2 becomes, v2 means what is that? C by n2 by v1 is nothing but c by n1. Now if you simplify that equation, c by n2 into n1 by c, then c gets cancelled, n1 by n2 is to be obtained. Means sine theta t by sine theta I equal to v2 by v1 equal to n1 by n2. What is this n here? N is nothing but index of refraction. Hence, this law is called as Snell's law of refraction. Okay. So from this we have got two relations. One is Snell's law of reflection and Snell's law of refraction. So Snell's law of reflection case, theta I equal to theta r. Now it is Snell's law of refraction. Refraction means that refracted wave is also called as transmitted wave. Hence, it is the ratio transmitted to the incident. And the sine theta t by sine theta I equal to v2 by v1 equal to n1 by n2. This relation is called as Snell's law of refraction. Why we call this as refraction means it is derived from the index of refraction. And as we know that index of refraction is represented with n, and it is given by the ratio of velocity of light in free space to the velocity of light in that particular medium, right? So depending upon that, sine theta t by sine theta I equal to v2 by v1 equal to n1 by n2. Okay. So till now we have got four relations. One is sine theta d by sine theta I equal to v2 by v1 equal to n1 by n2 equal to, and it is also equal to beta 1 by beta 2. As beta, we know that is phase constant of the medium 1 and medium 2 respectively given by 1 and 2, beta 1 and beta 2. Okay. Next. Now one more relation, to get another relation with the permeabilities. Now for a non-magnetic medium, as we know that mu is the permeability of the medium in magnetic fields. That's why for a non-magnetic media, we will consider the condition as mu1 equal to mu2 equal to mu naught. As we know that mu naught is permeability of the free space medium, right? And we know that its value also, that is 4 pi into 10 power minus 7 Henry per meter. Okay. So for a non-magnetic media, mu1 equal to mu2 equal to mu naught. Now from this relation, we know that velocities in general, velocity formula is given by velocity. The medium is velocity equal to 1 by root of mu epsilon. Right? So from this relation, we have got velocities v1 and v2 are given by v1 equal to 1 by root over mu1 into epsilon 1, nothing but 1 by root of mu naught into epsilon 1. 1 by root of mu naught into epsilon 1. Similarly for velocity v2 equal to 1 by root of mu2 into epsilon 2, which is nothing but mu naught into epsilon 2. Right? As we know that velocity v equal to, this is general formula, 1 by root over mu epsilon. Now from that v1 equal to 1 by root over mu1 epsilon 1, nothing but 1 by root over mu naught into epsilon 1. Similarly, for velocity v2 is 1 by root over mu 2 epsilon 2. Now from this, the non-magnetic media is given by mu naught into epsilon 2. Okay. So as we know that v1 and v2 relations with the index of Snell's law of refraction. Now put those two v1 and v2 values in that particular equation. Now sine theta t by sine theta I equal to v2 by v1 equal to n1 by n2 equal to beta 1 by beta 2. Till now we have derived. Now consider any two relations. So I am going to consider these two are the general relations. Now sine theta t by sine theta I equal to velocity v2. v2 means what is that relation? 1 by root over mu naught into epsilon 2 by 1 by root over v1. 1 by root over mu naught into epsilon 1, which is equal to 1 by root over mu naught into epsilon 2 into root over mu naught into epsilon 1. Okay, so mu naught and this mu naught gets cancelled. Root of epsilon 1 by epsilon 2 is obtained for the case of sine theta t by sine theta I. Okay, so this is also one of the relation for this Snell's law of refraction. So sine theta t by sine theta I equal to v2 by v1 equal to n1 by n2 equal to beta 1 by beta 2 we have obtained. Now from this one more relation as root over epsilon 1 by epsilon 2. Okay. Now one more characteristic parameter is left out, that is intrinsic impedance of the medium. So to derive that, intrinsic impedances can be expressed in general eta equal to root of mu by epsilon for a dielectric medium. Why? Because for a dielectric medium, sigma equal to 0. As we know that intrinsic impedance in general formula is j omega mu by sigma plus j omega epsilon. Characteristic parameter formula for the intrinsic impedance of lossless medium, dielectric medium or perfect dielectric medium is eta equal to j omega mu by sigma plus j omega epsilon. Now if you substitute sigma equal to 0 for the dielectric medium, root over j omega mu by, if you substitute sigma by 0, j omega epsilon is left out. This gets cancelled. Root over mu by epsilon is left out with the formula for intrinsic impedance of the lossless dielectric medium or perfect dielectric medium, right? So in general, this is the formula. Now we want to calculate for the medium 1 and medium 2 separately. Hence, eta 1 can be written as root over mu 1 by epsilon 1. For a non-magnetic medium, mu 1 equal to mu 2 equal to, just now we have seen for a non-magnetic media, mu 1 equal to mu 2 equal to mu naught. Right? Now if you substitute mu 1 by mu naught by epsilon 1 root over this thing and eta 2 equal to root over mu 2 by epsilon 2. Now if you substitute mu 2 by again mu naught and epsilon 2, then this becomes means sine theta t. What is that general formula? Sine theta t by sine theta 1 I equal to. So just now we have seen that is epsilon 1 by epsilon 2 as got from the non-magnetic media case, right? So if we equate means one more relation v2 by v1 equal to n1 by n2 equal to beta 1 by beta 2 and r. Now consider any two relations sine theta t by sine theta I equal to, or if we substitute eta 1 by eta 2 first. Eta 1 is what? Eta 1 by eta 2, or let it be eta 2 by eta 1. How we have got means eta 2. What is that? How are you going to derive this one? Eta 2 means what is that relation? Root over mu naught by epsilon 2 by eta 1 root over mu naught by epsilon 1, which is equal to root over mu naught by epsilon 2 into epsilon 1 by mu naught. This mu naught and this mu naught gets cancelled. Root over epsilon 1 by epsilon 2 is left out. So this is nothing but what is that relation? Eta 2 by eta 1. So finally we can conclude for that Snell's law of refraction with all the relations, how we have evaluated is sin theta t by sin theta I equal to V2 by V1 equal to beta 1 by beta 2 equal to N1 by N2 equal to eta 2 by eta 1 equal to root over epsilon 1 by epsilon 2. Okay, so this is the way Snell's law of reflection and Snell's law of refraction can be evaluated from the oblique incidence at a plane dielectric boundary. So for the dielectric boundary case, we have considered both the mediums are two dielectric medium. As we know that for a dielectric medium, sigma equal to 0. Now characteristic parameters are given for the medium 1 and medium 2 as epsilon 1 mu 1 for medium 1 and epsilon 2 mu 2 is for medium 2. Now from that we have got Snell's law of reflection first equal to theta I equal to theta R. Angle of incidence is equal to angle of reflection. And another relation that is Snell's law of refraction. So this refraction is also called as transmission, and the refraction is nothing but here sin theta t by sin theta I equal to is the ratio of to theta t to theta I. Now we have got these many relations from the velocities v2 by v1, from the phase constants beta 1 by beta 2, from the index of refraction n1 by n2, from the intrinsic impedances eta 2 by eta 1, from the permittivities root over epsilon 1 by epsilon 2. This is called Snell's law of refraction. Okay, why it is called Snell's law of refraction means it is derived from the index of refraction, and in general that index of refraction is represented with n and it is given by c by b, where c is the notation for velocity of light in free space medium and v be the velocity of light in respective medium. Okay, so n is equal to c by v, that is called index of refraction, hence the law is called Snell's law of refraction. Okay, now from this oblique incidence at a plane dielectric boundary, we also have one more relation called critical angle. To get this critical angle, first we need to know what actually total internal reflection, right? So that is called, now to get total internal reflection, that is x here z in the incident wave strikes the boundary, that is incident wave, and this is reflected wave, and part of this is called transmitted wave. Transmitted wave. To know this total internal reflection means the complete incident wave is reflected back to the same medium itself, is called total internal reflection. Means there is no transmitted wave which is aligned on the or exist in the medium 2. So medium 1, this is medium 2, right? In order to calculate this total internal reflection, first we have to consider this one, Snell's law of refraction condition, that is sin theta t by sin theta I equal to, I'm going to consider according to the densities, that formula is epsilon 1 by epsilon 2. So consider here medium 1 is more denser than that of medium 2. And this is the case theta t means is equal to 90 degrees. Consider medium 1 is more denser than that of medium 2, and this theta t transmitted wave making angle is equal to 90 degrees. If sin theta t equal to pi by 2 and theta I equal to, consider it as theta c. Okay, now if you substitute here theta t equal to pi by 2 and theta I equal to theta c. Now in place of theta t, if you consider pi by 2, in place of theta I, if you consider theta c, now this relation is obtained as sin 90 by sin theta c equal to epsilon 1 by epsilon 2. Sin 90 is 1 by sin theta c equal to root over epsilon 1 by epsilon 2, or from this sin theta c equal to root over epsilon 2 by epsilon 1. Now from this I am going to calculate this critical angle which is represented with theta c, and it is given by sine inverse of root over epsilon 2 by epsilon 1. Okay. So theta is represented with the angle and c stands for critical angle. Okay. So how we can define this critical angle means the critical angle is the angle at which the total internal reflection takes place. When the total internal reflection takes place means when the medium 1 is more denser than that of medium 2, when theta t is equal to 90 to 90 and theta is assumed to be theta c case, total internal reflection takes place. Means at theta t equal to 90 degrees means this transmitted wave is aligned exactly on the particular axis. This becomes theta t. Right? So this is the case. The entire incident wave is reflected back to the same medium. There is no transmitted wave. Right? This is the case. The process is said to be total internal reflection. Total internal reflection means this is the case. Theta, there is no transmitted wave which is aligned in the medium 2. So when theta t equal to pi by 2, this will be aligned on exactly on x-axis. If you still increase the value of this incident wave more denser, hence it will become means the entire transmitted wave or the entire incident wave is again reflected back to the same medium. Right? So this is the case. Critical angle and total internal reflection we have discussed. So what do you mean by critical angle? Means critical angle is the angle at which the total internal reflection takes place, and mathematically we can represent that theta c is equal to sine inverse of root over epsilon 2 by epsilon 1 is equal to sine inverse of eta 1 by eta 2. Like that, the rest of the relations are to be written. Right? So theta c is said to be here critical angle, and based upon total internal reflection, we can define this critical angle. Means critical angle is the angle at which total internal reflection takes place. So when the total internal reflection takes place means if the medium 1 is more denser than that of the medium 2 case, transmitted wave is aligned on the exactly axis. So that is the case. Total incident wave is reflected back to the same medium. Hence, in the medium 1, we have two waves, incident and reflected wave. There is no transmitted wave in the medium 2 case. That concept is called as total internal reflection. The angle which is to be obtained from that is called critical angle. Okay. So, in this lecture, what we have learned is the oblique incidence at a plane dielectric boundary. From that, we have derived Snell's law of reflection, and that is given by theta I equal to theta r, and Snell's law of refraction, that is sin theta t by sin theta I equal to V2 by V1 equal to N1 by N2 equal to beta 1 by beta 2 equal to root over epsilon 1 by epsilon 2, nothing but beta 2 by beta 1. These are all different relations which are considering according to the propagation wave, electromagnetic wave characteristics. Based upon all the characteristics, we have got Snell's law of reflection as theta I equal to theta r, and Snell's law of refraction as the sin theta t by sin theta I equal to n1 by n2. Why particularly we have considered n1 and n2 only means it is derived from the index of refraction. And also we have learned critical angle and total internal reflection. That is theta c is given by sine inverse of root over epsilon 2 by epsilon 1. The angle at which the total internal reflection takes place is called critical angle. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.